Hi. Today we are going to continue studying potential energy diagrams, and we're going to see why they're so helpful to chemists. And there's two very important pieces of information that we can get from them, and they are the activation energy and the heat of reaction. So first, just a quick review of what we learned last lesson. Potential energy is energy that is stored in the bonds between the atoms. And when we talk about endothermic or exothermic reactions, gaining or losing energy, the energy that they're gaining or losing is coming from or going into the bonds. So and they all have a very similar shape where they either have more or less energy at the beginning. This reaction, because it has more energy at the beginning on the reactant side and less on the product side, it means that it's losing energy. So this is an exothermic reaction. If instead the products had more energy than the reactants, then it would be endothermic because it would have been gaining energy. And whether it's endothermic or exothermic, it's always going to have a hump in the middle because you have to add energy to break the old bonds. And then as the new bonds are formed, that releases energy. And in this case, it releases more energy than we put in to make it. So the three new things that are on this sheet, or on this page of the notes. First, there's a name for that middle part of the reaction, that moment where the old bonds break and the new bonds form. So here we have just a couple of atoms. Let's say this is like H2 and Cl2. We have hydrogen gas and chlorine gas combining together to make hydrochloric acid. So first we've got them in the proper orientation. They collide together with sufficient energy, and in the moment that the bonds between the atoms are breaking, there's new bonds forming. And that moment is like the highest energy possible that's stored. Like all of these bonds as they're forming and breaking have a ton of energy. And that in-between state is called the activated complex. After that, as the new bonds form, they separate out into their lower energy products. So that middle part is the activated complex, and that's always at the very top of the peak, no matter whether it's endothermic or exothermic. So the other two pieces of information on this diagram that we're going to be looking at is activation energy and heat of reaction. So activation energy is the official term for the energy that we need to add to break the old bonds. And this is always going to be a positive energy because we always have to add energy to break the bonds. So a real life example of this, of an exothermic reaction, would be combustion. Burning things is exothermic. We know this because heat comes out of that reaction. So we have the ingredients to the reaction right here. We have fuel, we have oxygen in the air. Collisions are happening, but nothing's actually going on. And that's because there's not enough energy to break the old bonds. So when we strike a match against a matchbox, the friction, watch me not be able to do it. Look at that. That's embarrassing. I'm keeping that in. I'm not going to restart the video. We're just going to laugh at me. Now I'm mad. I don't care if this is a bad YouTube video now. I'm going to get this stupid match to make a real flame. There. There. So what we needed was friction to provide that little bit of energy to get us over the hump. And once we're over the hump, then the reaction releases enough energy to keep the reaction going and keep it letting the other atoms get over the hump. So that's the activation energy. I hope you enjoyed that interlude. So the other energy that we're looking for in potential energy diagrams is the heat of reaction. The symbol for that is triangle H, Remember, triangle stands for delta, or the change. So this is like the change in the overall heat. That's the way you can think about it. And that's the difference between the reactants and the products. And this can be positive or negative, depending on if it's gaining or losing energy. So whereas the activation energy cares about how much we have to add to get over the hump, the heat of reaction ignores the hump completely. The heat of reaction is just, I started at one energy, I ended at another energy. What's the difference between them? It's like the net, the overall change. So the symbol for that is delta H. By the way, the symbol for activation energy, this is chemists being chemists, scientists in general, they put the A afterwards and as a subscript. So this is like the energy of activation. Sorry, that's just how they do it. Okay, so what you'll have to do on your assignment is, if you're given a potential energy diagram like this, you'll have to tell me what's the energy of the reactants, the products, the activated complex, and also what's the activation energy and the heat of reaction. On the y-axis, the scale, PE stands for potential energy, and that's in kilojoules. I think we talked about that in the year. So remember the chemicals that we start at an energy level of 70. So our energy of the reactants is here in the middle at 70. The products are where we end. That's all the way down at 20 kilojoules. And then the activated complex is the very highest peak. That has an energy of 100. So that's how you find reactants, products, activated complex. So remember, the activation energy is the energy you have to add to break the bonds. So if we start here at 70, and we have to get up to 100, how much do we have to add to get there? And I just did something. And I don't know. So we have to add 30 kilojoules to go from 70 up to 100. So for this reaction, which once again is exothermic, we have to add 30 kilojoules of energy to break the bonds. But the energy that is lost is more than that. So the heat of reaction, remember, is going to ignore the hump. So we're going to just kind of ignore this hump and say, okay, we start here at 70, we end down here at 20. How much is just that difference? From 70 to 20, how much did we drop? So ignoring the hump, that's the activation energy. What's the heat of reaction? And in this case, from 70 to 20 is 50. And because it's going down, we say that's negative 50. A negative sign is a way of showing that it's losing. And that's it. That's how you would do it. Let's do an example with an endothermic reaction. So this has a similar shape with a hump in the middle, but in this case, it's gaining energy. Energy is going into it. Once again, the energy that we start with is the energy of our reactants. The energy we end with is the energy of the products. And once again, that point at the very top where the old bonds break and new bonds form, that's the activated complex. So our reactants are at 100-ish. Our activated complex is at 250, and our products are at 200. So for this reaction, the activation energy is much larger. We have to go all the way from 100 all the way up this hill to 250. So that's a pretty big activation energy. In this case, from 100 to 250 is 150 kilojoules. Our heat of reaction is the difference between where we start down here at 100 and where we end at 200. So that goes from our products up here at 200 to to our reactants down here at 100. So the difference between them is 100, and because it's gaining energy, that's a positive 100. So yeah, that's how you can find information using potential energy diagrams. Based on the shape and the scale, you can figure out whether it's endothermic and exothermic. You can figure out how much energy you have to add to break bonds and what the overall energy gain or loss would be. The last bit of notes is just a lot of time, like sometimes you won't be given a diagram and all you'll be given is the value of delta H, like this number here. And you can tell based on the sign whether it's endothermic or exothermic. Negative means losing, exothermic, and endothermic would be positive. I hope that was helpful. Let me know if you have any questions. Have a wonderful